Hello, everyone. Today's topic is going to be the moment of inertia. And it has its origin in something really familiar, which is the idea of mass. Mass, after all, is nothing more than the total and complete sum of every element, molecule, compound, Bloody Mary that's inside of an object. You just add it all up, and that gets you mass. We just learned about the concept of center of mass, the idea that this simple little scalar quantity of ours can be thought of as, rather than being distributed, that it has a center, that all of the mass, when averaged, is around a center. So we saw the R center of mass, the center of mass location, was just given by summing up every location with every mass it had. The moment of inertia is going to take the next step. The moment of inertia is going to say, let's sum up every little piece of mass that we have, its location, but now squared. So now we're not getting a picture of a balance in terms of the center of mass being where the center of gravity acts. But instead what we're looking at is this idea that how an object's mass is distributed can be quantified, because I've taken the square of its location. The plus or minus portion of it goes away. So we wind up with this thing called a moment of inertia. And naturally, it has an integral form, r squared dm. And we might do some examples with the integral form, but by and large, you're engineers, which means what you do is you look that up. You look up the value of the moment of inertia. Second thing you should notice is the moment of inertia is not a vector, which means it's a scalar, which means you're tempted to just want to add it up. But the moment of inertia can vary depending upon the axis that it's rotating around. So we'll do a real quick example of that. Let's say that we've got two simple masses, a distance L apart, and the other mass is a distance L apart. We'll make the masses equal to make our lives easy. But I'm going to anchor this setup here in the middle and this setup here off to the side. And when I'm careful, I will label it as the axis. So let's derive the moment of inertia. In this case, I, around its axis A, is given by 0, right? It's in the middle, right? Nah, you guys got me on that one. I've got the first mass, L over 2 squared, plus the second mass, L over 2 squared. So I'm going to wind up with, let's see, 2 over 4 ml squared. Let's grab the next one real quick. This one has an axis, so we do I equals the mass 0 squared, yay for zeros, mass L squared. So this is going to reduce to ml squared. Two objects. Two identical objects rotated around a different axis. The one on the left, we're rotating it around the middle, so it's kind of like a baton or a dowel rod, anything you're going to spin around the middle. A pencil for all you guys who can, and girls out there who can do that little trick. But if we nail one end of it down, allow it to rotate, but nail it down, we get a different moment of inertia. So, while the left one is greater than the right one, the implication here is this is easier to spin because it has the lower moment of inertia. Comparatively, when you have a moment of inertia of ml squared compared to 1/2 ml squared, this is going to be harder to spin. So I've brought in the idea of spin all of a sudden. And what I'd like to do is show you why this moment of inertia comes in handy. So let's go back to our spinning object. We'll do one we've done so we know the answer for it when we see it. Let's see, that has to go red. And we'll go about the center again. Okay. So now what we're going to do is apply some velocities. So we'll get this one spinning, which means this one has to spin down this way. And with our length L between the two masses, which again we'll keep identical, these velocities become tangential velocities that I can write the kinetic energy then for each of these guys. Alrighty, so let me erase the squaggle there. And this is 1/2 mv squared. And I'll add to it the other 1/2 mv squared. And as far as the rotation goes, what I have here then is, let me keep the, let's put them together, and I'm going to get an mv squared as my total kinetic energy. But we know that we can't, we know that there's a relationship between the velocity and the angular speed. So this thing's going to go around with an angular speed omega. So let's drop that in, and we're going to get m r squared omega squared, or mr squared omega. You know, this is so close, it's just tempting. If I group this together, I'd have I'm so close to having the moment of inertia. Boy, if I just had that 1/2 out there, oops, and yes, thank you, that's omega squared. What I'd wind up with then is going to give us the kinetic energy of these two rotating bodies. So I can then write that the kinetic energy of rotation will be equal to 1/2 the moment of inertia omega squared. So back to what we do know is this is playing the role of velocity. Even though it's the angular velocity. And the I then is playing the role of mass in rotation, which we've given the fancy name, it's strictly a fancy name now, of moment of inertia. All right. That's a quick, easy intro. We'll work some problems later.